So, we are going to start a new topic today. We are going to look at boiling. So far all the processes, heat transport processes we looked at, we assume that the heat transfer is occurring from, let us say, solid to a single phase or from a single phase fluid to a solid. So, what we are going to see is in boiling, what happens is that there is a phase change which is involved. So, there is a phase change which is involved in boiling process, and in fact, the same thing is involved in condensation, which will be the next topic that we will look at. So, in boiling, in addition to heat transport, from, let us say, solid to liquid, we will also have latent heat So, it is not just the sensible heat, so it is not that just the sensible heat that controls the heat transport process, it also the latent heat of the fluid controls the net amount of heat that is transported. So, what we are going to see is how to incorporate latent heat in the heat transport calculation, and we retain our original objective. The objective is to find the heat transport coefficient, okay, H and H bar. So, those are the objectives. Now, suppose if we have a fluid, okay, and this is something that all of us have encountered sometime, like boiling water. We have always done that. Right? So, if you take a beaker, take any container, okay, so I am going to supply heat, I am going to heat the bottom of the container, okay, and I have fluid which is sitting here. Okay. So, the question we want to ask is, what is the net amount of heat that is transported from the solid to the fluid? Now, it is not just enough to say solid to fluid, we have to qualify it with something else, and the reason is that the fluid is now boiling and there is change in the phase of the fluid. So, the fluid is now going from, so this is the vapor state of the fluid and this is the liquid state of the fluid. So, therefore, the net amount of heat that is transported, it depends upon what fraction of this fluid is going to be in the vapor state. So, therefore, we will have to now incorporate the extent of vapor which is formed inside this beaker in our heat transport calculation. So, it is not enough to simply know what is the amount of latent heat, but it is also important to know what fraction of the fluid is converted to the vapor state, because there is latent heat which is involved here, and so whatever heat that is supplied from the surface of this container, the bottom surface of this container, let us say that I know I can maintain this, let us say at some surface temperature Ts, okay. So, I keep supplying heat, and whatever energy that is supplied to the surface is now taken up by the fluid, and the fluid sensible heat is going to increase, and moment it reaches the boiling point or the saturation temperature at the given conditions, some fraction of this fluid is going to get converted into vapor phase. Now, if I continue to further heat, there will be more fluid which is going to become vapor, and that is what we have observed when we actually heat water in our kitchen, right. All of you must have seen this, either you have done it yourself or at least you have observed this, where when you heat something, you will always see that at different time points, although you can still maintain at the same temperature and you can maintain constant, you can provide heat at a certain flux, you will see that the amount of vapor which is being formed is actually varying, right, as you supply heat to this container. So what we are going to see in today's lecture is, we are going to see how we can attempt to find heat transport coefficient based on what are the different types of boiling. Okay. So there are, based on the fraction of the fluid which is converted into vapor phase, you can classify the boiling process into 4 different types. So we are going to first describe what are these different types of boiling stages, and we are going to see how to capture the heat transport coefficient for each of these stages. So in order to do that, we need to first look at how to perform a controlled experiment. Okay. A controlled experiment was performed, and the way the controlled experiment was performed is, instead of heating from the bottom of the container, okay, a platinum wire was placed inside at a specific location, just slightly above the bottom surface, and then you provide to electrically heat the platinum wire, and so you will start seeing vapors which is formed. Okay. Now, because the vapor is lighter, they are going to travel through this liquid and they will start moving towards the upward side, and the liquid is going to displace it, right. So therefore, clearly one can see that there is a natural convection process which is involved. Clearly natural convection is involved here, because the fluid particles which are actually going into vapor state is now going to be lighter, and so they have to be displaced, and so that sets up a natural convection motion. Okay. Now, the second thing is, it's obviously going to be a function of the surface properties. Particularly the nucleation process. We'll see a little bit more details about these in a short while. So the bubbles which are actually nucleated on the surface where the heat is being provided to the fluid, so you will see that the nucleation is a strong function of the properties of the surface. So if the surface is very rough, then certain locations are preferred for nucleation over other locations in the same surface. So the surface roughness and other properties, they play a strong role in boiling process. Okay. So before we go into the details, one of the important things is that it's almost impossible, it's very difficult to formulate governing equations. Now, it's not impossible to do that. The only reason is that you are not introduced to two-phase flows. Remember that it's a two-phase system. So if you know how to characterize two-phase system, which is beyond the scope of this class, we should be able to write governing equations. But let's assume for now that it's not very easy to do that given the background of this course. So one way to look at it is, but still we can get some intuitive ideas as to what is going to happen. Okay. So the way to look at it is, so suppose we want to perform, or we want to find what are all the dimensionless quantities which are involved here. Okay. So what are all the dimensionless groups involved in boiling process? What are all the dimensionless groups that are involved in the boiling process? Because all the convection topics that we have seen, we always found that there is a relationship between the Nusselt number and the dimensionless quantities which is actually characterizing the transport process, whether it is heat transport or mass transport or momentum transport, right. So therefore, if we know the dimensionless groups, then we can get some clue as to how to find the heat transport coefficient. Okay. So what we are going to use is we are going to use the dimensional analysis. We are going to use the Buckingham Pi theorem, which has been taught to you in your fluid mechanics class. So the heat transport coefficient will be a function of what are the different properties or aspects of this problem, which is going to decide the heat transport coefficient. Yeah. What are the different quantities or properties of the fluid which is going to influence the heat transport coefficient? So remember that all the dimensionless numbers we got, they are combination of sub properties of the fluid, right? So the objective is to find out what are these dimensionless groups. So you need to know what are the properties of the fluid on which the heat transport coefficient is depends upon. Right? That's the objective. Right? So remember that you always found, for a general system, you always found Nusselt number is some function of Re and Prandtl number. Right. So this is what we found for all the systems we have looked at so far. And Reynolds number uses the properties of the fluid and captures the momentum boundary layer behavior, and Prandtl number captures the thermal boundary layer behavior based on the properties of the fluid. So similarly, so from here you can clearly see that heat transport coefficient is a function of some combination of the properties. So if we can identify what the properties are on which the heat transport coefficient is going to depend upon, we could actually do a dimensional analysis and find out what is the dimensionless group by using the Buckingham Pi theorem. So what are the properties? Density, okay. So that's, yeah, Cp, density, the capacity which tells you what is the sensible heat that the fluid is going to take, conductivity, Kf, okay, yeah, latent heat. So Hfg is the latent heat of vaporization of the fluid, okay. So we got 4. Viscosity, why? Because of natural convection. Then yeah, temperature. What temperature? Is it surface temperature? So remember that we are looking at the amount of heat that is transported. So that depends upon? No, it depends upon the temperature difference, which is the difference between the surface and the saturation temperature. That's the boiling point of the fluid. Okay. And then what else? Yeah. Yeah, but particularly when we are looking at boiling, assume that the fluid is actually at the saturation. So that's okay. Yeah. Yeah. What else? So natural convection. So we said viscosity, but what else? Gravity, right? Somehow the buoyancy has to play a role here. Right. So it will be G times rho liquid minus rho vapor. So that tells you what is the force, body force difference between different locations in the fluid, and that exhibits the buoyancy, right? So how many are there? 1, 2, 3, 4, 5, 6, 7. What else? That's it. Obviously it depends upon the length of the wire, right? So you need to know what's the length of the wire. Okay. Anything else? Yeah. Because the amount of area that is available depends upon the length. So the length scale tells you what's the area that's available for heat transport. So it has to be a function of the length. Remember, Nusselt number, you have h into L by k or d by k if it's a polar coordinate system. Okay, what else? We've got viscosity, we've got sensible heat, we've got rho. This is another important aspect. So, okay, I'll give you a hint. Okay, suppose if the vapor is now forming at the surface of the wire, okay, that's already taken into account because buoyancy tells you the difference in the density, so that's good enough. Now, suppose you have a vapor bubble which is formed at the surface of the wire. Now, the extent of heat that is carried by the vapor depends upon what factor? Cp of the vapor, but something more than that. You need to have a contact, right? So, you are looking at heat transport from the wire to the fluid. Okay? So, it is a strong function of the surface tension. So, if the surface tension plays a very strong role in actually defining what should be the extent of contact of this fluid with the wire. So, you have 10 different factors which actually play a role in defining what is the heat transport coefficient. Okay. Alright, so I won't go into the details of Buckingham pi because that has been covered in your fluid mechanics class. So, if you use the Buckingham pi theorem, so you will get 5 dimensionless groups. So, that will be Nusselt number equal to HL by KF, and that will be a function of G rho L rho V L cube by mu square, comma Cp delta T by and mu Cp by K, which is Prandtl number, L square by sigma. Okay. What is Cp delta T by HFG? HFG is the latent heat. So, that tells you, so this is called the Jacob number. That is the ratio of maximum sensible heat divided by latent heat. Okay. So, it is the ratio of the sensible heat that is carried divided by the corresponding latent heat. So, this tells you what is the fraction of the heat that is supplied to the fluid particle is carried as sensible heat and what fraction is actually used for phase change. So, whatever heat that you supply to the fluid is what is being used for transport of heat via sensible heat and also for change in the phase. Okay. So, the last one is called the bond number. So, that BO, this is Prandtl number, you know that. So, bond number is the ratio of buoyancy forces to surface tension forces. Okay. So, that is the bond number, and so these are the 5 dimensionless groups that will come out of the Buckingham pi theorem. I think all of you should actually try to get these 5 groups. You go back to your fluid mechanics notes where you've been taught how to derive these dimensionless groups and find out what these 5 dimensionless groups are from, starting from the fact that the heat transport coefficient depends upon these 9 factors here. So, there are 2 classes of boiling. Okay. One is called the pool boiling and the other one is called the forced convection boiling. Okay. So, it might be a bit surprising to see forced convection here. So, we will see that although the fluid is not being pumped or it is not being forcefully made to flow or something, but you will see that there is a certain type of forced convection which is involved, and we will actually discuss it very briefly when we go to that topic. Okay. So, in pool boiling there are 2 types. One is called the free convection mode, the other one is called the nucleate boiling, nucleate pool boiling. Okay. So, what was observed, this experiment was done by a person named Nukiyama. So, what he observed is that because it is a very controlled experiment, okay, it is a very controlled experiment, you can find out what is the net flux of heat that was actually, or net flux of energy that was transported to the fluid. So, you made a plot between Qs and delta T. Okay. Now, here we assume that when you start the experiment, the fluid is almost at the saturation temperature. Okay. So, this is Ts minus Tsat. So, note that saturation temperature is fixed for a given fluid under given conditions. The saturation temperature or the boiling temperature is fixed. So, what he observed was something like this. Okay. So, we are going to explain in a short while, we are going to explain why you get such a curve and what is the significance of this. So, suppose so this is the kind of curve that he obtained, and what was observed is that there is a maximal heat flux, okay, on the curve, and there is a minimal heat flux in that curve. Okay. So, this is what is called as a boiling curve. This is what is called as a boiling curve, and the location up to which the maxima appears, this region before that is called the pool boiling region, and this region is called the transition region, and this place is called the film boiling region. Okay. So, these are the three different stages of boiling.